In Chapter 13, we talked about some basic concepts of temperature and its molecular explanations. In this chapter, we will talk about heat, its concept, its effects, and the methods by which heat is transferred. You might still remember this example from last chapter's PowerPoint. We know that by thermometer, the temperature of these 3 toilet seats are the same. But why we all tend to feel that the metal seat in B is the coldest, while the seat with the cover in C is the warmest? Our feeling has a reason, and the reason is the human body is not a thermometer, and it does not feel or sense temperature. What it really feels is the flow of heat, or the heat transfer. Generally speaking, during a cold winter night, the temperature of the toilets is lower than the human body, so one feels the bigger heat transfer from the human body to the toilet with the metal seat, because metal has a larger thermal conductivity. If two objects at different temperatures are brought in contact with each other, that is, energy is able to flow between them, the energy will be transferred from the hotter to the colder objects until equilibrium, that is, when the two objects are at the same temperature. Please note that there is no work done here by either object, yet there is a change in energy. The transfer of energy is caused by the temperature difference, and it stops when the two objects have the same temperature. This spontaneous transfer of energy due to a temperature difference is called heat Q, and its SI unit is joule. Q is a scalar, but it could be a positive or negative value. When heat goes into the system of interest, the Q is positive. When the heat goes out of the system of interest, the Q is negative. One of the major effects of heat transfer is temperature change. Heating increases temperature, while cooling decreases it. If we assume that there is no phase change and no work is done on or by the system, the quantitative relationship between heat transfer and the temperature change is Q equals to mc delta T, where Q is the symbol for heat transfer, m is the mass of the substance, and delta T is the change in temperature. The symbol C here stands for specific heat and depends on the metal and phase. The specific heat is the amount of heat or energy necessary to change the temperature of the substance 1 kilogram of mass by 1 Kelvin. The specific heat C is a property of the substance, and its SI unit is joule over kilogram times K. Here is a table of the specific heat of some substances. Let's look at this example together. We know that the pen and the water are always at the same temperature. Since we know the temperature difference, we can calculate the heat using the equation Q equals to mc delta T, while delta T equals to 80.0 minus 20.0 equals to 60.0 degrees Celsius, which is the same as 60.0 Kelvin, because this is the temperature difference. And we have the heat used to raise the temperature of the pan equals to the mass of the pan times the specific heat of the aluminum times temperature difference, and we get 27.0 kilojoule. Since the volume of the water is 0.25 liters, and that is 0.25 times 10 to the minus 3 cubic meter, we calculate the mass of the water to be 0.25 kilogram, and the heat required to raise the temperature of the water equals to 62.8 kilojoule. We add these two together and get the total heat equals to the heat for water plus the heat for the pan, and we get 89.8 kilojoule. Now we calculate the percentage. The percentage of the heat used to heat the pan is 27.0 from here divided by the total heat, and we get 30.1%, while the percentage of the heat used to heat the water is 69.9%. It is also possible to change the temperature of a substance by doing work. Work can transfer energy into or out of a system. This realization helps establish the fact that heat is a form of energy. Let's look at this example together. If the brakes are not applied, the gravitational potential energy is converted into kinetic energy of the truck. When brakes are applied, part of the gravitational potential energy is converted into internal energy of the brake material. Since the brake material only retains 20% of the energy from the truck going down 75.0 meter, so that the heat transfer to the brakes equals 20% times the gravitational potential energy, mgh. Well, h is 75.0 meter because it says it's in vertical displacement. And we get 1.47 times 10 to the power 6 joule. Then the temperature increase of these 100 kilogram of brake material is delta T equals to Q over mc, where m is 100 kilogram, c is 800 joule kilogram times degrees Celsius, and we get 18.4 degrees Celsius. You might be familiar with this picture if you have ever had an ice box when you go to the beach in the summer. Like an ice box, a container that prevents heat transfer in or out is called a calorimeter. And the use of a calorimeter to make measurements is called calorimetry. And the key point here is that inside an ideal calorimeter, the objects are thermally isolated from their surroundings. Since there is no heat transfer in or out of the calorimeter, if we have cold objects such as ice cubes and hot objects such as the Coke inside the calorimeter, due to conservation of energy, the heat given by the hot objects plus the heat absorbed by the cold objects should be 0. Let's look at this example together. In this example, it says that the pan is placed on an isolated pad and there is negligible amount of water boils off, so that the heat transfer only occurs between the pan and the water. And we can view the whole system of pan plus water as a calorimeter. Since the final temperature is the same, we have Q hot equals to the mass of the pan times specific heat of aluminum times the T final minus 150 degrees Celsius, and Q cold equals to mass of the water times specific heat of the water times TF minus 20.0 degrees Celsius. Please note that here it is okay to keep the degrees Celsius as the unit of temperature because we know that the change in temperature in the unit of degrees Celsius is the same as the change in temperature in the unit of Kelvin. And we may also notice that since T final should be lower than this 150 degrees Celsius, this term Q hot is actually a negative term. Combining these few equations, we have the Q hot part plus the Q cold part equals to 0. And we can solve for final temperature TF. We have this expression, and we plug in all the numbers. We get 59.1 degrees Celsius. So that's the final temperature of the pan and the water.